in class we measured the temperature versus time of approximately an ounce, a small swallow of water in a styrofoam container. I heated that up in a microwave, and we put a temperature probe into it and read the temperature off of a computer, essentially. So we started with the temperature 61.5 Celsius. Over a period of several minutes we fell to 42.3 Celsius in a room where the temperature was 23 Celsius. The temperatures observed at 1 minute intervals were 61.5 first observation, and 58.1, 55.2, and so forth. And I've written those as a sequence which I've labeled S. S equals this sequence of temperatures. What we noticed was that, the way we did this exercise, we took the first reading, we took the second reading, then we asked people to calculate or to predict what the third reading would be. Most people predicted, well, since temperature fell 3.4 degrees here, it ought to fall about 3.4 here, so we ought to end up a little less than 55 degrees. The 55.2 didn't surprise those people very much because, as we know, anytime we observe something there can be little fluctuations in data. And a lot of those people repeated their prediction and underpredicted this temperature also, until they started realizing that, well, these temperatures seem to be changing by less and less, and really if we stop and think about it, that's kind of what we expect. As the temperature gets closer to the room temperature, we expect it to change less and less quickly. That's kind of what this graph shows us, that the temperature starts out changing faster, but then the slope of the graph gradually decreases as we approach room temperature. Now this isn't an accurate graph of the data, but this is kind of the behavior that we expect and sort of the behavior that we observed. Most people, because every minute, during the minute, I asked people to predict what the next temperature would be. So we had approximately a 10-minute exercise in predicting the next temperature. Most people got pretty good at this, and most people were doing something very much like this. We take the S prime sequence, which we've defined to be the set of differences of this sequence, the difference sequence, and we see that that's 3.4, 2.9, 2.6, 2.2, 2.0, and so forth. Clearly, the differences are decreasing, and by looking at the pattern here, we can usually predict what the next difference is going to be. Now this last difference, we went from 1.8 to 1.7 to 1.5, then dropped all the way to 1.1. I think I've commented in the notes that water behaves in kind of a funny way. You get layers, temperature layers, even in a small sample of water, and these temperature layers can sometimes invert and throw off what's really happening. A potato, a Bing cherry, a large grape makes a much better subject for observation than a little bit of liquid water in the bottom of a styrofoam cup. In any case, this is the data that we got, and what we expect in a situation like this, and we didn't really get it here, but we expect that the data will be modeled very well by an exponential function when the temperature of an object approaches room temperature.